Assalamu alaikum. Last year, I got fascinated with gardening. And because I'm a fan of green tea and because I like mint a lot, I decided to get a mint plant in the apartment where I live. So I started taking care of it, irrigating it. But after 1 week, my little mint plant died. And I felt so sad that I want to be able to make my favorite tea again. So would you like help me, guys, to sort out my problem? Think with me. Why does my plant die? Is it because of the water? Is it because of the quantity of the water or the quality of the water? Is it because of the nutrient? Is it because of the soil type? Or what are the possible reasons and scenarios? Okay, I would leave this for you to think about it from now till the end of the class, and then later on, we can know the exact reason. So let us start. In today's lecture, we're going to learn about the importance of soil water to plant. We're going to also learn about the properties of the water and how the water moves into soil. And also later on, we're going to learn how to quantify the soil water potential. Without further ado, let's begin. Why water is important? As mentioned in the Holy Quran, that life is made from water, and without water, nothing can grow and nothing can be sustained. Water is very important for plant growth. It's also very important for the nutrients. So the plant is able to uptake the nutrient from the soil also because of the water. We have seen that water is very essential component for the weathering, particularly the chemical and the physical weathering of the soil, which leads to the development and the formation of soil. Water in many cases also can cause soil erosion. And because of the water and because of the differences in the soil properties, some of the soils might hold different amount of water than the others. Water is a very unique substance. It's a dipole, which means that if you look at the water molecules, you find that it consists of two positively charged hydrogen and one negatively charged oxygen. And because of the angle between them and because of it, water is so unique, is a dipole. It has a negative side and a positive side. Because of this, water is able to attract to water molecules through what we call the cohesion forces, a hydrogen bond, and water is also able to attract with the other substances and the surfaces. And water is able actually to climb in a tube, for example, or to move into the soil or to move inside the plants due to the adhesion and the cohesion forces. And this is an example how the water here is attracted to kaolinite, one of the types of clays that you already get familiar with in this course. Because of the properties of the water, water acts as elastic membrane. I guess lots of you have watched this before, that we can see some of the small insects walking on the water. Water becomes an elastic membrane because of the adhesion and the cohesion forces. And water is able actually to climb tubes due to the capillarity. Now, if we want to understand the capillary force better, we can look at this figure here below. The capillary rise is actually what enables water to move against gravity in tubes or in soil. If you want to understand it more, it can be described by this equation, where h is the height of the capillary rise is equal to 0.15 centimeter cube over the radius. And we can see that the smaller the radius, the higher the rise. The same concept can be applied into the soil, where if you have coarse texture soil like sand, the rise would be shorter as compared to a fine soil. And we can see from this graph that two things I want you to observe, that we have here three different textures: coarse texture, something in medium, and another one fine. And we can see that the finer the texture, the higher the capillary rise would reach. But there is another very important thing that I would like you to spot your attention to is actually the speed of the rise. As you can see that in coarser texture like sand, the curve is so sharp. It means that it rises in very short time and it reaches its maximum capillary rise. Whereas in smaller textures where the water has to pass through irregular pathways and through very small pores, it takes them longer time to reach the maximum capillary rise, but it would have higher capillary rise as compared to coarse texture. Now, how the water moves into the soil and what are the forces that control the movement of water into the soil? If you want to understand this, we have to stop at our basics in physics. We know that energy flows from high potential to low potential. The same things can be applied for soil, where water moves from high potential energy to low potential energy. If you look at a waterfall, here at the highest elevation, the energy is very high. And if you look at the bottom here, you have a lower energy. That's why the waterfall flow from the high elevation to low elevation. Now, how these things can be simplified in the soil? Well, let's first stop at here. Let's first look at the adhesion and the cohesion forces and what does these two forces do for the soil? Well, because the water is held tightly into the soil, you need actually to exert force to move this water. The same things like when you apply and when you try to remove the water from a sponge, you need to squeeze the sponge, and by this the water can be removed. The same things can happen for plants. For example, when plants want to absorb the water from the soil, they have to exert energy that would enable them to move the water to their body and then to the plant. And if you compare the movement of water in free water body without soil, then it will be like more free as it compared to the one in the soil. Again, the soil would actually attract the water molecule tightly, and therefore you need energy to move them from the soil. Now, what are the energy that's responsible to control this movement into the soil? Well, we have the concept of the total water potential. And the total water potential into the soil is described by this equation. So you have the gravitational potential, the pressure potential, and the osmotic potential. The summation of all of these potentials would make the total water potential. And remember again that water moves from high water potential to lower water potential. Let's try to understand the first one, the gravitational potential. Well, the concept of the gravitational potential is very simple, that the gravity actually attracts the bodies toward it, to the earth, downward. This is the same thing that happens for the water molecules and to the soil. And this becomes more important when the soil is completely wet. Now imagine you are looking at the soil where all the pore sizes or all the pore spaces are filled with water. And here you have your point at the higher elevation and here you have the low. So what happens that the water moves from here all the way downward under the effect of gravity. If we want to understand also the effect of gravity, we have always to consider an arbitrary baseline. If this is a soil profile and here below you have a wet zone and here you have dry zone, and if we assume that our baseline is here, so anything here would be considered as 0. Anything above the baseline is considered positive, and anything below the baseline is considered negative. But the most important thing that I want you to understand from here that the gravitational potential becomes very important to move the water downward under the saturation effect, exactly like what happens here. Now let's look at the other force, the metric potential. The metric potential actually describes the addition and the cohesion forces. Because of the attraction between the water molecules and the pores and the solids, the water is held tightly into the soil. If the soil is very dry, then the metric potential becomes more negative. And if the soil becomes wetter and wetter, the metric potential becomes almost approaching zero. Under a full saturation, when the soil is fully saturated, the metric potential would be zero. Here, the water moves from high potential to low potential. Again, if you assume this is a wet area and this is a dry area, the water moves under the effect of metric potential from the wet area, which has the higher total potential energy, to the dry area, which has the lower total potential energy. I mean, negative. So it moves from positive to negative. Another important concept of energy is the submergence potential. And this becomes very important when you have a saturated zone and a non-saturated zone, like the conditions, what you can see in this one. So if you actually put a pressure gauge and you try to measure the pressure here, you can see that under the water table or at the water table, the potential or is zero. Below it, as you go down, as you can see here, it's increasing. So the potential becomes more positive and it's increasing. If you go above the water table, then actually the energy is decreasing. Sometimes the submergence potential and the metric potential are combined in one term called the pressure potential. Another force is actually the osmotic potential. The osmotic potential becomes very important when you have actually salts into the soil. Now, let's consider the example of the school experiment that we did. Basically, the osmotic potential becomes more important when you have a semi-permeable membrane. If you have a semi-permeable membrane and you have here an area with low salt, pure water, and here high salt, the water moves due to the osmotic potential from high potential to low potential, from the pure water to the salts. And maybe that's the reason why, for example, plant dehydrate under saline conditions. So under saline condition, the water moves from the plant's body to the soil. It moves from actually the pure water toward the high salt content. It moves from high potential to low potential. Now let's think a bit. Do we have really osmotic potential in the soil, or is it really very significant? Well, this determines if we have actually a semi-permeable membrane. And in fact, we don't have permeable membrane into the soil. But this becomes very important when we want to describe the movement for water from actually the soil to the plants, because the plant roots would act as a semi-permeable membrane, and this becomes very important. Now, let's look at the water as a quantity. If we look at the water can be described as quantity, the amount of water, and it can be determined by the gravimetric or volumetric. Gravimetric expression is mass over mass. So it's actually the mass of water in mass of soil. The volumetric moisture content is actually the volume of water that exists in a specific volume in the soil. The potential is basically the energy, and it can be described as bar or kilopascal. How can we determine the soil water potential? Well, we can do this in the lab or we can do it in the field. If we start in the lab, there are certain techniques like the pressure plate or the thermocouple cyclometer. And in the field, we have something called the tensiometer. If we look at the pressure plate, I guess you have seen this in our soil lab. And the pressure plate is actually looks like the pressure cooker where we cook meat. Now, let's look in details at the pressure plate apparatus. In the pressure plate apparatus, you actually have a pressure chamber, and you have a porous plate there, ceramic plate. And then you have actually the soil sample, and you have here outlets. What you do actually, you place the soil samples here, and then you subject it to certain pressure. Under this high pressure or under different pressure condition, the water would be removed from the soil samples. And then you can measure the amount of water that exists in the soil after you drain the water, and you get the value of the pressure and also the value of the amount of water content. And this later on would help us to determine what we call it, to build the retention curve, which can be used to manage irrigation, as you would see in the next lecture. So again, in a simple way, this is how it looks. You have actually a pressure chamber, this one, and then you have here actually a ceramic, and then you put the soil samples, and then you subject it to certain pressure, let's assume 1 bar. And because of this, the water would be removed from the pores outside, and then you can later on, after 24 hours, you take the sample and you measure the amount of water content left into the soil after the removal of the water under the pressure, and you know the value of the pressure. So how much water existed under 1 bar of pressure. And here actually a video which would show you the experiment.
Okay, for the second part of lab 2, we're going to test the wilting point pressure, which is 15 bars. And to do that, instead of using the Tempe cells, we're going to use a pressure plate extractor. And this has one really large O-ring. You want to make sure that there isn't any dirt, sand, or soil on it, that you clean it really well. Then you take vacuum grease and you cover it around the entire ring, and you place it right into the top. And this is going to make a seal once you close the lid. And so what we're putting in the bottom is a big ceramic plate. Just like we did with the Tempe cells for lab 2, we had the little tiny ceramic plates. We soaked them in 0.01 molar calcium chloride overnight. We do the same with this. We soak it overnight. And then what we do is we take these little tiny metal rings and we place them on the plate, and you're actually going to take the soil that we're testing right now. We had them in the soil cores for the Tempe cells. We're taking that same soil and we're pouring that into the rings. All right, just like that. You don't want to pack it down or anything. You want it to be sort of in its natural state. You want to make sure that, just like with the larger soil cores, that it's even across the top. And once you've got them all filled, you're going to take the same solution that we soaked the plate in, the calcium chloride, and you're going to saturate the core. Then we take the plate and we place it down in the bottom. Right, and we connect this hose to this. It's going to push out the water that we have inside the plate and inside our little mini soil cores. So you shut this. Then I'm gonna put a beaker here to collect the water that's gonna be pushed out. And then we have it connected here, and all we do is we just turn this on and turn the pressure up to 15 bars. And we let it sit for about 3 days, is about how long it takes. And then once that's done, we open these up, take the rings off, and then empty the soil into an aluminum pan, weigh it, put it in the oven overnight, and then weigh it again to get the water content at 15 bars.
So that's actually the idea. So what you do, actually, you calculate the amount of moisture content that you have under each pressure point. So you repeat the experiment several times. You repeat it, let's say, with 1 bar, then with 5 bars, or 3 bars, 5 bars, 10 bars, 15 bars, and so on. So that's the idea. The other tool that can be used to measure the water potential into the soil is called the tensiometer. So what is actually the tensiometer? The tensiometer, in a simple way, is actually here, as you can see. So it's actually, it has a porous tube, and it has here a tube that would be filled with water, and it has a pressure gauge. So what you basically do, you fill this one with water and you remove the air from here. You suck it, so the gauge would read 0. Once you insert it into the soil, then it will start the experiment. So what happens that, because the soil is dry and this is wet, completely filled with water, so the water moves from the ceramic to the soil. And as it moves to the soil, from high potential to low potential, it actually creates suction. And this suction would move actually the pressure gauge and get the readings. Because of using of this device, you would be able to know when to irrigate your soil. If the soil is closer, let's say, to a certain point, then you know that you don't have to irrigate. If it's getting drier, it reads here high potential, and because of that you have to apply water. The last device is what we call the thermocouple cyclometer, and it looks like this. This device actually measures the relative humidity in the soil, and it actually different than the other two devices because this one can give us the metric potential plus the osmotic potential. So it can measure the effect of salinity into the soil. And by this, you would be able actually to determine the amount of water content, and you can manage the soil. Now, let's come back to our story. Did you figure out the reason? I will tell you what happened. Actually, I was using a sandy soil. And you know that different types of soil holds water differently. So what happens that I went over the weekend, I irrigated the plant before the weekend, and then I left for the weekend at home. And then when I come back, the water was already evaporated from the soil. What it means that this type of soil needs frequent irrigation. And because of that, the plant couldn't find water into the soil, and therefore it wilt and died. So that was the reason. So you have now to be very careful to know that different types of soil will hold water differently, and therefore you need to apply irrigation at a different frequently for each types of soil. Now I would leave you to enjoy with a final video that would use the concept of capillary to make beautiful things with flour, and here you can make your own business. I hope you enjoyed the lecture and enjoy the video.
Bearded Sense Guy here, and today I'm going to show you how to change the color of flowers using food coloring. To start with, you need a group of white or beige colored flowers. Now cut the stem at a 45-degree angle. In an empty container, add 200 milliliters of warm water, 1 teaspoon of sugar, 1 teaspoon of white vinegar, and 15 to 20 drops of food coloring. Remember, the more food coloring you add, the darker the coloration will be in the flowers. Once the contents are mixed well, now add your flower to the container. The reason this works is that flowers have vascular tissues called xylem, which transports water and minerals up the stem to the flowers and leaves, where the water evaporates, leaving the food coloring to get darker and darker. Thanks for watching Bearded Science Guy. If you enjoyed this video, check out some of my others, or subscribe on YouTube and Facebook.